All right, I guess we'll go ahead and start. I'm sure people will trickle in as we go. Welcome everybody to the CEE Environmental Graduate Seminar. Just as a note, if you want credit for this for continuous learning, just email Dr. Eric Segrin and he can get you an official notice that you attended today's seminar. So today we're honored to have Dr. Zhanping You from Michigan Tech. He earned a Ph.D. in civil engineering from the University of Illinois at Urbana, Champaign in 2003. He's been at Michigan Tech, promoted to professor in 2014 and distinguished professor in 2019. He has completed many research projects related to road materials, pavement engineering, and sustainable building materials. His contribution to pavement and materials research has led to journal articles, book chapters, and advances in engineering practice. He's led research projects from engineering practice of roads to pavement science with funding from federal, state, and local agencies. He's received numerous recognitions. For example, the U.S. Department of Transportation's Dwight David Eisenhower Award Fellowship. He was awarded Dwight Davis Transportation Faculty Fellowship. He won Michigan Tech Research Award in 2019, named Fellow of ASCE and Fellow of International Association of Advanced Materials. He served as the chair of ASCE Engineering Mechanics Institute's Pavement Committee and Bituminous Materials Committee. And he's been a guest editor for other journals outside of ASCE. So with that, Zhanping, take it away.
Thank you, Ryan. Well, it really is my honor to talk in the department in environmental engineering grad seminar, and of course, really most of my research work really is. So I always feel like I always really think there are a lot of things for me to learn from my environmental engineering focuses. So that's the reason we're here. I like to present some work I have been doing, and there are some of the components really is by working with some of our environmental faculty. So my work really is dealing with from recycled materials and from research to practice. So probably I like to really give you some kind of a introduction about some work I'm doing. So basically, roughly there are 4 components here. It's basically introduction of research goal and in-house research and or modeling part of research, and then to the demonstration projects. So how we land our development, and then a brief summary. So first, let's take a look at the scrap tire. So basically, you and I are driving. If you drive, of course, after some years, you close your tires, right? Basically, this is this is the newest data we have, just published a few days back by U.S. Tire Manufacturers Association. So basically, right now, basically, well, of course, 2019. So basically, this is all the scrap tire. Where is it going to go? You can see the majority part, of course, 37% are basically be burned as a tire-derived fuel. Of course, you can imagine what you are going to do with the tires if you burn it. Of course, you probably can imagine there's some smoke. I saw those things basically only from TVs, how they really burn tires. But of course, tire-derived fuel probably should be a little more cleaner. And you can take a look at that, ground rubber. That really means they are cutting the tires to pieces, make it as rubber particles. And there are some applications of that. Next one of civil engineering application, 5.15% roughly, maybe just, this is very general applications. And land disposal, as about 14% of the tires are disposed in landfill. And of course, there are 10% other applications, such as you can use that, export it, or other type of applications. And my major thing, I like to focus on this 24%, okay? This is ground rubber. Out of this, ground tire rubber, how much really we are going to we're going to do with it. Let's take a look. So out of the 24%, then there are most of the things, 35%, used in the molded and extruded industry, and also some are used on the mulch, and of course some are used on sports surfaces like tracks, playgrounds, that kind of applications. And there are only 17% really using asphalt. Of course, you can imagine this is only 24% of the entire U.S. rubber, tire, scrap tire, basically eventually going to go, but only 17% out of 24% are in asphalt. So really that really means in asphalt itself, in the entire scrap tire market is really small components. However, this application here, of course, I think there are a lot of advantages, and not only in engineering application advantages, also environmental beneficial. That's the reason we're trying to, my job here is basically trying to promote the use of scrap tires in asphalt. All right, so all this data are from there, of course, I like to really see, how really we can better use scrap tires. Let's take, so here is basically a few pictures here. In the past years, we have been using different applications, with tire rubbers. One, of course, we are calling, it's called the dry process, some wet processing. And we basically, tried all the, those technologies. And so basically, for example, in the wet process, we did some kind of research project here in, in-house, and also we placed, some kind of pavements, in the site. Kuna County, there's a project in Muskegon County, in downstate, basically which is a wet processing approach, and also we use the dry process in a few locations, like a Kalamazoo and also Dickinson County, and also next one is going to be Grand Rapids next year. So this is some of the work I'm doing. So for example, this is scrap tire, you can see, and we grind two different, particles, pieces, and then we can have some kind of treatment. We can deal with it. We can use that one for different applications. So basically this one is basically some work I did when I was in Texas. When in US-Mexico borderline, there were tons of scrap tires at that time. There are still, so this is some pictures here showing, they are trying to, process these tires by bale it up. You can see after bale it look like this. So basically each one maybe have 50 some tires together. Use steel wires to, wrap it together. Of course, by doing that, of course, there are some of the advantages. Of course, one is you use less space, right? Because, those kind of tires use up a lot of space. And also, this one also can squeeze the most of the space so that there are rattlesnakes or, some kind of those things are not going to live here. That is, this one, of course, in Brownsville, Texas. And look at this one. So basically we have all those tires baled like this, and we could not find ways to, to use it. Of course, make this one as rubber. At that time, it's kind of expensive. Okay, and also you may cause some other environmental issues, and of course cause fire as well. So this is basically one thing about the tire bales, and we are trying to use this one just for road construction. For example, one piece of this application we did was for the landfill roads. Basically, they need to have kind of the roads, but of course in South Texas, really no much aggregates, no much stones. What you can do? You can buy stones from Asia or from Alaska or from Canada. So this is basically partially solve the problem with less, need of aggregates. So this, of course, one of the applications. You can see this one almost like a pass through a swamp. Really, you need some kind of materials to use. This is the one application we did. Of course, this project was supported by EPA, and I was basically part of that process. And this one here basically showing you the scrap tires over the years. It's a good thing, it's going to be declining, but of course, every year we have more tires really being generated. So this is basically one of the things I like to show you. So it's not that scary. However, there are a lot of scrap tires are coming out. So that is basically some of the general things what we are trying to do. We're trying to use up the tires, okay, and through our research and development. So recycled rubber research, there are a few components here. I like to really briefly share some information with you. These three pictures here, basically showing you the three typical pavement failures. So this one, the first one here is rutting. So basically, rut like this is not really fun to drive in winter, especially here in UP, right? It's when you have snow or some ice and on the roads, especially plus on the rutting, this is very dangerous. And of course, with the low temperature crack, this one, it really happened all over the place. Basically, not only really in Michigan, it's also happened in some other places like Florida. You have it's basically their crack, of course, when you have crack, of course, when you drive on it, you can feel that it's not very comfortable. Of course, fatigue cracking is another deal. It's also just makes your pavements like a fractured. So that is not really good, right? Basically, these are three typical pavement failures to avoid. And of course, our goal, of course, trying to do is make sure the roads are, have a good low temperature crack resistance. So basically no crack, right? Well, that's our goal. And we don't really want to see much fatigue on the roads, no rutting, no moisture damage. Of course, like this picture here, you see here, almost like, this is like, of course, it's a joke, but really showing you what the moisture damage look like eventually. First, just a really small amount of aggregates are lost in, and then eventually that piece gets bigger and bigger and bigger. Then you can basically almost like raise the fish on the middle of the roads. That's basically happened a lot. I experienced a few of those things just the last a couple of days. Next time, basically I like to do is basically showing you some of the experimental program they have here in Kalamazoo County. So this is the project we did. Basically, we use a lot of rubber, and in this material we use a lot of rubber. You can see in this type of in the scale you see here. So basically, we treated this kind of rubber with some fillers and with asphalt as well. So basically, we put that in the asphalt plant and they pave it under roads. All right, this is really in 2018. And I want to show you a little bit more information about that kind of process. Of course, for this type of research and the development, there are something a lot of lab work we need to do. For example, I called it the first one called performance testing. So performance testing, of course, we mainly means one is low temperature crack and testing. So make sure there's no much of low temperature cracks. The other is no much ruts, okay? And then of course, moisture resistance. So basically, we're trying to make sure the roads are free of moisture damage. And in performance analysis aspect, we will take a look at all the statistical analysis from our test data to make sure that the data is meeting the agency's requirements, for example, MDOT requirements. And the numerical simulation is basically trying to help us to make sure a certain of ingredient design or structure design are going to meet our road use. And of course, either eventually, no matter how good the experiment work in lab look like, how beautiful the curve look like for numerical simulation, eventually our work need to land in the field. That's basically something we're trying to do. So all my work eventually should really go to the field, should find applications. Okay, so basically, this is something about for the field testing. That's something we are going to, I'll show you in a few minutes about some of the application of field performance measurement and noise and ride quality. Here is a few examples about our lab testing. For example, here is basically we call one of the APA testing called asphalt pavement analyzer. You can see this is some kind of pavement cores. You can call it pavement cores, or this type of materials we produce in our house, in lab. Then basically we have rubber hose application, and you basically apply loads on the top of that one with multiple cycles. Of course, the temperature is controlled here. For example, the temperature here, it's a pretty hot summer day, and basically you can see we generate this much ruts, right? It's something you can see. We have another set of equipment called hamburger wheel tester. You can see the samples was like this. After testing, you can see how much depth of the ruts we have. So of course, you know, there's something we have seen here. You can see on the pictures on the right-hand side is this one is a sample without rubber, this one with the rubber. So we really want to see what the difference is. Okay, what's differences that we can see. But of course, this is some kind of I personally call this maybe called a torture test. Torture test basically showing you how good it is from your eyes. You can see that. And we also do some testing, for example, like a split tensile test. This, of course, split tensile test, almost like an indirect tensile test for concrete. There are a lot of similarities. You can see eventually when you load the sample, crack it normally starts cracking from a center, similar like those two pictures you see here. Of course, we also did a bunch of numerical simulations, like the pictures on the right-hand side using a numerical simulation method, or we call the discrete element method. So that is basically for the experimental, some of the experimental work we did. And another unique one we did here, basically called fracture energy testing. Here you can see this test chamber we have. The sample is going to be like a cylindrical sample, 6-inch diameter like this one. And we cut a notch here, and then drill 2 holes. And then of course we cut this portion off so that we can measure, attach our strain gauge on it. So basically we load this sample, we load those 2 eyes, and then we want to see what is the load and a CMOD look like. So basically in general, it's load displacement, okay, how that really curve goes. So when you stretch it, when you're trying to do the testing, you can see the curve eventually going to look like this. So load versus CMOD. And we can just, from this curve, we can find out the area underneath this curve. Of course, we can use a lot of ways to calculate that one. So basically, this area here really is called fracture work. So let's say if rubber asphalt versus non-rubber asphalt, of course, we assume rubber asphalt, we'll have much higher fracture work. That means in order to crack the sample, you need a lot of work or a lot of energy to crack the sample. So we'll see what the results look like over here. You can see here a piece of results I have here is average fracture energy, and versus a lot of some other samples you can see here. And control 1 and control 2, basically these are basically the normal asphalt we use on the roads, like say US 41. Here is basically roughly use those kind of dense graded asphalt materials. You can see their fracture energy about 400 joules per square meter. And the rest of those bars actually with a certain of rubber inside. Of course, depends on sometimes more rubber, less rubber. Let's ignore those things. You can see roughly the results about 1200 joules per square meter. What's that really number tell us? It's tell us with rubber material inside, it's going to be 2 to 3 times higher of fracture energy than the control asphalt we're using. So that really means this is there are a lot of unique features for that. So that really means the rubber asphalt has a lot of advantages. So that is something I like to really show here. So that is basically, of course, give us some confidence. When this type of material is used in the cold climate like Michigan, the fracture resistance should be really good compared with the regular asphalt we are using today. All right, of course, with that one, we also, like I just mentioned earlier on, we also do some kind of a numerical analysis. And for example, most of my work really in the past was discrete element models. Of course, I sometimes also use finite element models. My discrete element models really has been really used over the years. I think we graduated a lot of students. And also, this also some of my PhD work. You can see some of the images I have here. So in order to simulate what the stones look like, we get some kind of numerical images of the stones. And we use different models to represent it. You can see, poor resolution, better resolution. Okay, just you can go on and on to make it really very accurate. So with that one, we generate some kind of a model, aggregate model libraries. So basically, we create those things through different techniques, and we can do a lot of simulations to see what kind of gradation is good. How much percentage of stones versus, let's see, bigger aggregates versus sand? What's the proportion we should really have, so that we have a better design? Okay, so basically, this is something we are running this type of simulation in-house, and of course, plus we also do some mechanical testing work in-house. And with that one, we basically can find out a good design for the mixed design. And a few examples like this here, for example, here is we also simulate what happened for this kind of test called disk compact shape testing, DCT. So what sample was like this, after crack it looked like this, all right? So, and with that, of course, I won't really, basically do some kind of simulation. For example, this one what the sample look like, and so what does the model look like, and what's the, after the during the tests, what's really the sample look like. And also we can also control a lot of things. Here is, this one, for example, no rubber on the top. This one no rubber. This one has some rubber. This one more rubber. This one a lot of rubber. 37. That means I have 3.7% rubber. 4.1%, 4.5%. It's more and more rubber. So the more rubber we have, supposedly we have higher fracture energies, right? That's basically something we, through our experiment, we found out that one. But of course, we also trying to make sure that is real, what happened from our expectation from numerical simulations. So that is basically something we are trying. And I get to maybe give you a sense of what's the testing look like. This one, no rubber, okay? For no rubber with the testing going on, you can see what's a crack happening. The dark lines, basically, the red lines, basically showing what that is. So basically that really means there are some cracks happening, right? So the red really basically crack happening between the asphalt, and the black happening basically is from stone and stone. So that is basically interface, they get cracked. But on the right hand, this one is with rubber, asphalt mixture with rubber. When you test this one, you can see this one take a long time to crack the sample. And even that, you can see a lot of different colors here. That really means the asphalt materials really cannot really be cracked all the way easily. So there are a lot of things, for example, like mastic, rubber, and those type of interface, they are pretty strong. So that is from that kind of fracture path, really basically we can identify, with the rubber, there are a lot of advantages to prevent the crack further going on. I want to really show you maybe another thing. Oops, I need to go back here. And also maybe just take a quick look at what the contact force really means. For example, when you have the testing like this one, it's just suddenly just really quickly without rubber. So basically the crack just happening, right through, okay, pretty quick. But with that's basically without rubber. On the right-hand side here is with rubber. That's with rubber, you can see the crack basically slowly being, the crack are basically trying to distribute more areas and more locations. So that really means the crack is not really going to propagate to all the way to the left easily. So basically there are a lot more resistance. So basically, of course, we can quantify all those parameters. So basically just want to really show you what really the general trend look like. Of course, we always analyze those data because this one is from numerical simulation. It's basically we call it discrete element work. And that is basically, of course, we did a lot of numerical work. We use university supercomputing facilities. Of course, that is some work we cannot do here. For example, for discrete element work, we have to use a small workstations. And this is some work I want to really briefly show you. For example, there's one project in Kalamazoo. You already see some of the pictures earlier on. So this project basically, the total is 3 miles long, and we break down to several segments. So 1.5 miles, basically for rubber. So a portion for rubber, a portion basically for non-rubber materials. You can see this was the locations. It's called West W Avenue. It's pretty busy roads and a speed limit of 55 miles an hour. And so basically before the paving, we have some preparations. You can see the existing roads got a lot of problems, a lot of cracks. So basically we have to mold it in. So you can see the top about an inch being milled off. So basically you take off the first portion and then you leave it's kind of like a really rough surface. When you drive on it, of course, it's really uncomfortable and very noisy, of course. But that's because for preparation for new layer of pavement, that's the reason we have to do it. So here, for example, how we really apply the rubber. This is the production facility of asphalt plant. And if for those who have been with asphalt plant, and you probably will know that there are a lot of this is cold feed beans. That really means all the aggregate, okay, stones. And you have probably had 10 different beans for stones. And for this illustration, I only have 4 here. But for this production here, I think we only really use 4 different aggregates. So coarse aggregates, finer aggregates, sand, stuff like that. And this place here is basically the asphalt. The asphalt basically comes from the refineries. So basically it's going to be stored here. It's going to be pumped inside, pumped to the mixer. Okay, so this one, dryer mixer is the most important component, useful component here, because this one is going to heat up all the stones to elevated temperature so that you can blend that one with asphalt very well. So, and when all these materials are completely ready, and so the material will be elevated to here to called storage silos, and the truck will basically haul the material from underneath the silos. All right, so that is normally the hot mix is going to be. So hot mix or whatever those mix, that's basically what do we do. So I think somebody did not mute yourself, so there's some kind of a little cracker noise. All right, so that is basically the dryer mixture components. This one is called the GTR band, so basically ground tire rubber band. This band was not, in the past, so people really don't have, use rubber here. So basically they use this place for recycled asphalt. So all the recycled pavements, from old pavements, they can put that to this place and go to the dryer, and then you can recycle asphalt. So that's the reason the asphalt industry, basically we recycle 100% of the asphalt. Okay, we never really, so right now, but the technology for today, we basically can recycle all the asphalt, from the roads. So right now for this project though, because we are using rubber, so we basically put the rubber here together with recycled materials together, feed here. So basically they are going to dry here, mix here, and then produce here, and then basically go back to the silo, and then truck will bring that to the job site. And from here, of course, you can see rubber being dropped from this bin here on the top. And then with the conveyor, it's just going to go to the mixer. Okay, so this was in the plant. Basically, we meet with different parties and the asphalt plant owners, engineers, and agencies. And there are also material suppliers, so asphalt suppliers, agri suppliers, rubber. So all kinds of people are meeting together to make sure the demonstration is successful. And when the materials bring to the site, you can see this is basically all our rubber asphalt project materials that you have. So you really don't really see, you don't really smell much about the rubber. Of course, we also control the temperature. We want to make sure there are not much of strong odor because the people really don't like that. So that is, of course, after the compaction, look like this road. It's pretty beautiful, and of course, the density has been measured. So basically everything be controlled. So basically all the construction is going pretty well. And here's, if you take a look at closer, and the pavement's a pretty good texture. So basically provide you good friction. And also, of course, it's a smooth with friction. Okay, that's basically something we like to see. And we also measure the noise levels. Okay, we basically we measured two different types of materials. You can see here I have one is called this is the material with rubber we have. Okay, or with rubber. This one overlay. So basically, really means regular asphalt. Okay, so basically like US 41. Okay, they use this kind of asphalt. Okay, overlay materials, and we measured all the different vehicle speed, like 30 miles, 40, 50, 60 miles an hour. Of course, like I said, the speed limit 55. Because there are a lot of red lights, stuff like that. So basically, people have to slow down for different reasons. So we basically would test different speeds. I did not test the high speed, really high, because I don't want to get the tickets there. So let's take a look at 50 miles per hour speed. So for the rubber asphalt, we get 76. And the conventional 77. Of course, it's a dBA. So, with that much difference, that's basically is very obvious. You can feel what the difference is. And you can see 40 miles per hour, 72 versus 73, 74, 75. That's very obvious. You can hear that one. So after the construction, and the neighborhood was really very curious. What do you guys did? It's very quiet. Of course, they were used to the kind of noisy roads in the past years. So right now, because the brand new rubber materials on it, so basically you really don't really feel much noise. And even compare with the new pavements, you can see this one new, this one also new, but the new rubber is even much better than the new regular asphalt pavements. So that is basically one project in Kalamazoo. And of course, we did a lot of lab work in-house for some other reasons. This is basically almost all the project team. You can see we work with different, partners. Of course, Kirsten from Eagle that time was not there. You can see this project when the, APWA, American Public Works Associations Awards. That is basically pretty nice, nice collaboration with those folks. And I also want to really show you a project with the Kuna County. This one was done in 2016 or 15. So basically, of course, in this project, we have two sections. Okay, one is in UP here in Kuna, the other is in Muskegon County in downstate. So basically, 2015. So this is basically both our terminal blend asphalt. That really means it's called a wet process. 12% of rubber has been used. We use a warm mix and a hot mix as well for both situations. I really want to show you really quick what's it look like. This is in Kuna County. So basically, the total experiment was pretty long. Was almost 5 miles. Okay, almost that much. Hot mix asphalt. Basically, this means the regular materials. Regular materials 2.5 miles. And this with rubber, it's called the chrome rubber hot mix, chrome rubber warm mix. So one is 1.4 miles and the other 0.8 miles. It's this type of experiments actually pretty big, right? It's pretty big. And of course, of course, construction cost is pretty high. For this project, I think eventually we spend, well, I'll talk a little bit later. So we test some other things as well. We tested the emissions as well. So of course, so the from technology paving, that section is basically with PI on it. So testing emission with Dr. Dave Hand was doing that, and of course with Dave Parham. So basically that is the few trials. I will show you some results here. So here is basically with the material we are doing for the for these two things. This is hot mix asphalt. This is warm mix, and of course with rubber mix as well. This is rubber hot mix. This one is rubber warm mix. So warm mix normally the temperature is about 30 degrees lower. So basically that really during the production, that means you are going to use less heat, less energy to be in the production. So that really is good thing, because you are going to have less emission to the air. That's something we care. So for example, in one project here is asphalt content 5.19, okay? This is asphalt content we are using, the new asphalt 5.19. But we use rubber for this material here, you can see it's become like 4.9 or so, okay, 4.9 basically for the with the chrome rubber. Because we have rubber inside, we pretty much really reduce the amount of asphalt. And for this one is similarly, okay, this is another project we did. This one was in downstate, we'll talk about later on. So the design asphalt content of 5.16. So eventually, if we are using rubber inside, we are going to replace that one a little bit. So basically a little bit less than 5.1. So basically we'll still save some asphalt. Not only use the rubber, we also save some asphalt. And of course, when we are using warm mix, we also save some energy to input. I also wanted to show you some of the results. Basically, this is eventually we are working together with Dr. Hand. So basically, you can see this is basically the emission of rubberized asphalt. With MDEQ at that time, EGO today. So basically, the limit was about 20 pounds per 1,000 tons of mixture production. So basically, that's much emission you can release. But for, of course, each individual ones, it's listed here as well. You know, for example, you have, benzene, how much, can be released. But in our production, this one, hot mix asphalt. This one is a rubber hot mix asphalt. This is rubber warm mix asphalt. You can see still we are meeting the requirement of state's test requirement for stack emission. Of course, this type of test is very expensive, okay, because we are going to test those kind of material in the plant. You have to continuously operate the plant for a certain of hours to continuously collect the sample and then test it. So basically, it takes a lot of effort. I also really want to show you another chart is showing you the benefits of different temperatures. You can see you can run the plant at 160 degrees C, 140 degrees C, or 120 degrees C. You can see, like, say, acetone, this kind of material released to the air. If you run it at the high temperature regularly, like what we're doing today, it's maybe roughly about 1250, nanograms per grams of materials. Those kind of emissions. But if you reduce the temperature, now you can see maybe this one about 300 or 350 or something, or 200 something. But when for all the elements, you can see like a xylene, for example, you can see this one here was like this high, like 2000 or something. You can easily reduce that one to less than 1000 when you reduce temperatures. So basically this one is only the 12% rubber inside, okay? So it's 12% rubber, and basically we can reduce the amount of emission if we are able to reduce the temperature. Of course, in order to reduce the temperature, we have to do something else, right? Basically, we cannot just randomly reduce temperature. Basically, we reduce temperature by using some of the foaming agent, for example, like water, or use some other chemicals. And so basically, we can reduce the operation temperature so that we can have less emission. And another one I want to really show you is the low temperature performance testing. Of course, you can see here's the load again, and then on the x-axis here is CMOD, which is the displacement during this test. So basically, every time if you do the test, if the area underneath of the curve is small, that means that the material is easily get cracked because it's require less fracture energy to crack it. And let's take a look at this one. It's one regular materials, this is US 41. Okay, let's assume this one US 41. And here is rubber asphalt hot mix. Here is rubber warm mix. I like to see what's really results look like. Of course, each test we have here, you see here is 3 replicates, okay? Because each time we have to run different replicates, at least 3. So the first one for the hot mix asphalt is 467 joules per square meter, and for the rubber, what is 2 rubber materials is 578 and 579. So that really, what that really means for this case, this is, of course, because this one was for a Kewanee County project we did. So you can see you have some bump on the fracture energy. That really means this material will perform very well in cold climate, okay? Or, not easily get cracked. So that is one of the things I like to really show here. And I also want to show you maybe the Muskegon project here. It's called Muskegon. Muskegon project is a little shorter. It's 1 mile. It's 1 mile, but this project actually is a lot of work. I will show you. This one is basically for the Cumana County. What's the plant look like? This plant is where? You folks know where it is? In Hancock, actually. This plant in Hancock. And this one, the construction was doing starting from here, US 41. Okay, it's basically this road is connected to US 41. This one place called the Gay Roads. Okay, called the Mohawk Gay Roads. So starting from the beginning, you probably saw the picture. You can see where it is. This one is basically they mailed it first, and then just place the overlay on it. So pretty easier operation. So this one, of course, we have a eagle, have the sign here. So we're showing that starting of the experiment. Basically, we have quite a few signs like this on this road after the construction. And of course, a lot of things, a lot of sampling work, a lot of testing work. You can see basically, we take some cores from the roads. You can see pretty messy afterwards. Of course, we have to clean up, make sure it's looking good. This one, after some years, some time, we will, keep watch it like a warm mix. Okay, this is a warm mix section. So, even today, still perform really good. I want to really briefly show you what the Muskegon County project look like. Muskegon County is basically, the project is over here. You can see what the plant look like. This one is a bigger plant. This plant operates like 400 to 500 tons an hour mix. And the construction, this one construction called a full depth reclamination. That means, so basically they take off the entire roads, they blend it and compact it again. And then on the top surface, add a new asphalt. So basically right now, this one already done. And then we add a new asphalt on the top and compact it, then it will be ready. Okay. So you can see, when they are placing about rubber asphalt here. So basically I interviewed all the, construction workers here to see if they smell anything, if they feel, is there any differences? So of course, they really don't feel this material has too much differences. Of course, maybe a little bit sticky, not bad. Dickinson County is basically, this one is a little bit bigger project. So this product is, we have two layers, two lifts. Basically, we have a layer underneath and a layer on the top. So I want to be a little bit quick since we are kind of out of time. For this project, of course, we have two different designs because, we have one is underneath layer and on the top layer. So we use a lot of recycled materials here. You can see 12% of regular stones, chip. We have natural sand, 22%, and manufactured sand, 33%. This means crushed sand. This is recycled materials, is industrial waste type of material, 15%. This material ISP really is like a roof shingles granulated. Okay, those kind of stones from the roof shingles. And the wrap is recycled pavement, recycled asphalt pavements. So we use 17% recycled asphalt, and on the leveling course we use 25% of that. So just want to let you know what's the ingredients look like. So basically we use a lot, trying to use natural materials because natural materials in general it's less expensive, and the recycled material is also our target. We're trying to use as much as we can. This is basically the overview of the plant in Dickinson County. It's close to Iron Mountain. This is a place. This is the unit we are using to pump our rubber into the plant. Okay, so basically pump it in the plant. This plant here is going to be hot, right? It's basically producing asphalt concrete. You can see this is after. This one is when the road bed is ready. So place on the top first layer, okay, and of course they have a second layer on it as well. You can see this fellow was trying to feel what the rubber asphalt look like, and he left some kind of a footprint on it on purpose. And of course, this one is after the first layer is done, and this one, of course, they have to open traffic all the time. So basically, some of the trucks can go through. You can see the first layer is done. This one, second layer is done. Okay, second layer, and then another layer will be next to the first one. This one is this side of this lake is part of Wisconsin, I think. It's a beautiful lake road. So this fellow is working here. You can see after construction, it's pretty smooth, and texture is pretty good. This project, for this Dixon County project, we used about 3,500 passenger tires, and Kalamazoo County, basically that one 5,300 passenger tires being recycled. And of course, this one, we also, through this collaboration, we also get the Impress Award. So here's Kirsten. She's with the audience today. So she's our strong partner from the state agency. She has been very supportive to our research effort. And here's Lance. He's Dixon County Road Commissions. I think that's it. Basically, I think, in summary, we did a tremendous amount of progress. So over the past decade, I think, from modeling, so basically we use discrete element models, finite element models, and in lab work, we test asphalt binder, aggregates, and asphalt concrete. And then eventually we move to the field practice. So over the years, I think we gained a lot of experience. So basically, we learned a little more and more, and basically trying to see how we can reduce the waste while we extend the pavement life. Of course, at the same time, we also pay attention to the emissions, energy assumptions, those type of things. And of course, in the performance-wise, we really want to make sure there's no much of moisture damage issues. Low temperature cracking resistance should be guaranteed. Noise level should be controlled. Basically, with all the rubber materials construction, eventually we always can find out the noise level will be reduced. That's a good thing. So that means a quieter roads. From a modeling, from numerical simulations, basically we can always do some work, basically, help us make a better design, or help us understand some of the findings we see in the lab. Sometimes we really don't understand, but from modeling, sometimes we gain some further knowledge. So with that, I really appreciate everyone's attention today, and thank you for the department's environmental seminar organizers time on inviting me here. Thank you for that. Of course, we have a lot of people to say thank you, but I know Kirsten is here from Eagle. Thank you, folks.
Well, thanks, Zhanping, and you can imagine lots of applause for you from the audience, even though virtually we can't actually applaud. But anyway, thanks so much for coming. Any questions from the audience from anybody?
Thank you, Audra.
Well, I just have one. Are there any environmental aspects of your research that you would like to do that you haven't had a chance that maybe someone in the audience could help with?
Yeah, I always have some questions regarding that. For example, lychee. Okay, for example, for a lot of times like road materials, after some years you get polished to get those kind of some particles may fall off. I always wonder, if there are any issues, how easy it is to measure those leaching potential issues, and of course there's also some filtrations and those things. Okay, that's one. The other basically about emissions. Okay, for example, we do all kind of experiments here, and especially with rubber, if you heat it up to temperature, to a certain time, for a certain temperature, you probably can smell something, right? Because sulfur compounds inside. So, there are a lot of rooms. I think, we can always work together. And for example, like image analysis, I think that's something, we can always find something to work together. I also think things like recently I talked with Ricardo, for example, for constructions, he can use his device and measure all the images on construction site. That's a great thing. That's so I think I pretty much think I'm pretty open to work with everybody, anybody, for every single thing. So you can always find something to work on. So I think there are a lot of rooms there.
I know when I drive past asphalt construction, it smells really bad. And I always wonder what's the effect on my human health from those emissions from the hot asphalt as it's being paved. So I don't know if you read anything about that, or has anybody studied that or those kind of things?
That's a very good question. That's a lot of people ask me too.
Yeah.
NIH did a study a few years ago. So basically, study not the drivers. Like you only drive through, right? There are a lot of people. Their time you spend really with those materials almost all day long. They are working like a 15-hour a day. Okay, especially in summertime, those guys work a long time behind the paver or in asphalt plant. Okay, so basically, the research find out, of course, those kind of steam is mainly come from water, and those odor you find, maybe there are some sulfur compounds which are not really going to make people sick, but of course you can try to avoid it. So of course, one thing you should really, I personally think, is dust. Dust is something is difficult to avoid. Even in the plant, they have a lot of features, a lot of things to do to make sure the air is clean and so that it can release right to the image send out. But there are still something they cannot do very well. So dust could be one thing. Other kind of chemical compounds, of course, there are some, you saw some images I showed earlier on. There are some compounds that are not really good, but those concentrations are so small that is not going to impact the human health. So at least that's from my understanding. And also with the EGO's requirements, so you can see, we are well below the limit. Probably we're not even 10% of the limit. So it's in general pretty safe. You can see I've been working on this type of material so many years. I'm so far so good.
Yeah. All right, thank you. Anybody else? Any students have any comments or questions?
Well, one thing I think is I should say that this is almost like my decades of research. I'm trying to package it together, and you informed me last week. I was trying to have everything shared today, so a little bit of rush, and so just apologize if there are anything missing.
No, I liked that it was a broad overview of many aspects of your research. And for me, that's what I needed because I don't understand the details anyway. So this overview was, for me, it was helpful. Anyway, we're a little bit past time, but we can stay. Does anyone have any last questions or comments? All right, well, if you think of things, you can always email Zhanping or strike up ideas or those kind of things. So thanks again, Zhanping. It was really great. I enjoyed it a lot. I'm sure others did too. So thanks again for coming. We really appreciate it.
Thank you all.
Thanks, Champaign.
Yeah, thanks.
Bye.
All right, thanks everyone for coming today.